Hello everyone, Rajeev here, chemistry master teacher at Vedantu, and we are discussing KVPY 21 essay stream paper. In part 1, the first question is, consider the reaction P aqueous in equilibrium with K aqueous with an equilibrium constant of 1.5. The reaction is started with a vessel in a vessel with concentration of 2 molar of P and 0 of Q. When the equilibrium is established, half the amount of P is removed and the reaction is allowed to re-equilibrate. The concentration of Q in the vessel at the second equilibrium. So initially the system, if I talk about the initial first equilibrium, then P aqueous and Q aqueous. So at T is equal to 0, 2 molar of P is taken, 0 Q, and when this attains equilibrium, let's say X molar P is reacted, so it will produce X molar of Q as 1:1 ratio is there. The equilibrium constant for this reaction is given as 1.5, so I can write this 2 minus, I can write this concentration of Q, that is X at equilibrium, upon P, that is 2 minus X at equilibrium, is equal to 1.5. When we solve this, the X value comes out to be 1.2, which means at equilibrium I have 0.8 molar P remaining and 1.2 molar of Q is produced. Now at this equilibrium, what has happened? Half of the P has been removed. So it again at time T, what we have done, we have removed half of the P. So we only have 0.4 molar of P and 1.2 molar Q in the solution. As we have removed the P, the reaction will attain equilibrium by moving in the backward direction. So let us say at second equilibrium, from 1.2 Y concentration of Q has decreased and Y of P has increased. Because it's the same reaction at the same temperature, K will not change. So K for this is still 1.5. So this implies 1.5 is equal to 1.2 minus Y upon 0.4 plus Y. On solving this, we get Y as 1.2 divided by 5. They're asking the concentration of Q. So the concentration of Q is 1.2 minus Y. So 1.2 minus 1.2 upon 5. This value comes out to be 0.96 molar. So the correct answer for this question will be option B. At the second equilibrium, the concentration of Q would be 0.96 molar.